In this video, we are talking about some examples that relate to our Week 8 of Math 277. So let's start things off with our very first question, number 1. Right, so we know that in order to start with a question like this, we want to find the tangent plane. We need to make our function equal to 0. Okay, so we are given our function of z with a fifth root. So if we add our power of 5 to each side, that gives us z to the power of 5, and this gets rid of our radical. If we move that over, this is x cubed plus y squared minus z5 equal to 0. So now we can start with our problem. And actually, we need to find our z. So we have our point, which is -2 and 3, but we don't have our point z yet. So we can use this equation. So yeah, so let's use this equation here. So z is equal to the fifth root of, so in our x we have -2 squared, and in our y we have, cubed, and we have plus 3 squared, and z is equal to, so this is -8 plus 9, so that's fifth root of 1, so that means z is just equal to 1. Right? It looks complicated at first, but if you plug in the values, you might find that it might be a lot simpler than you think. Okay, moving on. So this will give us our normal equation. So we'll start with 3x squared, and this is 2y minus 5z to the 4, and this is at our point -2, 3, and 1. And so our normal vector becomes, so this is 4 times 3, which is 12. This is 6, and this is -5. Okay, so now to find our tangent plane, you guys already know the drill. This is x, y, and z times the normal vector we just found, so that's 12, 6, and -5. And this is equal to our point, so this is -2, 3, and 1, times 12, 6, -5. Sorry, that's dot product with that, so this is 12x plus 6y minus 5z, and this is equal to -24 plus 18 minus 5. And if we move all of that over, this becomes 12x plus 6y minus 5z. And this is plus 11 equals 0. Right, so that is it for this question. Okay, so what if we had something like question 2? Sorry, let me scroll up, so let me just get rid of this. So we have room for question 2, because we already did question 4 in our last video. Okay, so question 2 is asking for points on a hyperboloid where the tangent plane is parallel to a given plane. So we have to kind of dissect what all of this means. So let's look at question 2. Let's use orange. Okay, so the first way to approach this is to find the normal vector to our hyperboloid. So this is going to be 4x minus 2y and 10z. Okay, but we're not given which point we want. So an important property to note, the way that we're going to do this has to be parallel to this plane here. So what we're going to do is take this normal vector, and it's equal to some kind of scalar k, scalar multiple of our normal of our parallel plane. Right, so if we take this normal, so if we use this logic, so from our previous one, from our hyperboloid, this is 4x, negative 2y, and then 10z, and this is equal to some scalar multiple of the normal force, the normal vector, which is 2, negative 3, and negative 10 of our given plane here. So that's to say that if these two planes are parallel, if I could draw it to the best of my abilities, that means both of their normals are going to point in the same direction. Right, but one just might be shorter or longer than the other, right? So that's why we have the scalar multiple k in there. So now we can make this equal to each x, y, and z term. So if we distribute that k in, this gives 4x equals 2k. This gives negative 2y is equal to negative 3k. And this is 10z is equal to negative 10k. Okay, and let's isolate for our x, y, and z terms. So this is x is equal to, so that's k over 2. And this is y is equal to 3 over 2k. And this is equal to, z is equal to negative k. So now that we've found our x, y, and z terms in terms of k, we're going to plug into our hyperboloid equation. So what that will look like, so this is 4, then x squared is going to be k over 2 squared. Oh, sorry, this goes into our original equation, not our normal. So our original equation was here. So this is going to be, so it's 2, then our x value is k over 2 squared. So minus y squared, so minus y squared is 3 over 2k squared plus 5, and our z was negative k squared, and this is minus 13 equals 0. We're going to solve for k using this. So minus 13 equals 0. So now we only have one term that we need to solve for. So this will be, so 2k squared over 4, this is k squared over 2, and this is 9 over 4k squared plus negative 5, sorry, minus 5k squared minus, actually I'm going to put equals 13, I'm going to move that 13 over. Okay, so this is 1 over 2 minus 9 over 4 minus 5 is equal to negative 6.75. K squared equals 13. I'm going to put this in a fraction form to make it easier. So this is negative 27 over 4 k squared. So 4. Right, and if we take 13, multiply by 4, divided by 27, and take the square root. So this is, okay, and this will give k squared is equal to 52 over 13, which is equal to 4. So k is equal to positive or negative 2. And when we plug this 2 back into our x, y, and z right here, we get, so this is, let's start with positive 2. So this is 1, and this is 3, and this is negative 2. And our second point with our negative 2 is negative 1, negative 3, and positive 2. So these are the 2 points where it is parallel to this new plane. Okay, so that is it for question 2. I'm going to skip over question 3, but feel free to work on it if you'd like. This is the same kind of approach that we used in question 2, so feel free to try it for yourself. Okay, and we're going to move to these questions over here. I want to try question 5. So let's work with question 5. Question 5. Okay, we need to find a unit vector that's orthogonal or normal to this surface given here. So let's make this equal to 0 first. Okay, and let's start with our normal equation. So this is, and then x, z, and then xy. At this point, 1, negative 2, 1, we plug that in. This becomes, so y is negative 2 times z, it's 1. This is negative 2. This is 1. And this is negative 2. Okay, so now what do we do going on from here? So now to find our unit vector for our normal. So remember, if we have a vector, a unit vector can be directed along the same path, positive or negative direction, with a magnitude of 1. So it's basically just in the same direction. So let's do that. And we know how to find our unit vector, which is equal to our vector over the magnitude of our vector. And since it could be going in either direction, we're going to add our positive or negative sign. So this is equal to, so it's negative 2, 1, negative 2, and it's plus or minus. And then this is equal, over, so that's square root of 5. No, it's not. Square root of 6. Sorry, I am going crazy. This is over square root 9. I'm so sorry. And this is equal to positive or negative. This is negative 2 over 3, 1 over 3, and negative 2 over 3. So this would be the answer for question 5. Okay, and let's move on to, let's see. Okay, let's try 7. Okay, actually I'm going to skip 7 for now and come back to it. Okay, so now let's work with differentials. So let's start with 8a. Now we said differentials were equal to plus our partial fraction of dy times dy. Okay, so if we did that just for a, df would be, specified at point A and B. Okay, so now we can actually use our delta x and delta y for this part. Okay, so this would equal, so this is exy and this is multiplied by y, and we're going to be using our points here. So this will be a minus x, and now this is plus x e to xy, and this is b now minus y. Okay, and that's if we use this specified point. But if we were just to write this in general, this would look like, so we can factor out our x to the y, and this is just y dx. If we kept our dx and dy in there, and this would be x dy. So that's a different way to write this. So we're going to stick with this form for our next questions. Okay, and let's do b now. So this is f is equal to, and this is yz dx plus xz dy plus our xy times dz. Okay, so that would be it for this question as well. Let's do part C now. So, actually, no, I will do part D. I'll have you do part C on your own. So, df, this is equal to, okay, so this is like saying, right, so if we did that, this would be, so this is negative 2x to the negative 3 for our dx term. For the dy, negative 2y to negative 3 dy. And this is negative 2z to the negative 3 dz. Okay, and let's factor out that negative 2. It's 1 over x3 dx plus 1 over y cubed dy. And this is plus 1 over z cubed dz. Okay, so that is this question done as well. Okay, so now let's do a couple linearization problems. So let's start with A. So we said that we would do plus our x1 and our delta x, and this is plus our partial y derivative of our function of x and y with our delta y. Okay, so, okay, actually I'm going to apply this to part B. Okay, so let's work with part B first. So this will be, okay, so it's our regular function, and this is going to be plus our new ones. This is chain rule, so that's 1 over 2 times x squared plus y squared plus 5 to the power of negative 1 over 2 times, and this is just with x, so this is 2x times our delta x, which I'm going to write in red, which is going to be our x variable minus our specified point a. Sorry, and in this example, ab is equal to 4, 2, so we're going to put 4 in for this part. And this is plus our y partial derivative, so it's 1 over 2 x squared plus y squared plus 5 to the negative 1 over 2 times 2y And this is multiplied by our delta y, which is y minus our b, which is 2. And so once we solve this, so we're going to plug in our a and b values for this part now, because those are our initial points. And we're going to keep x and y in these areas as their variable, but everywhere else we can plug them in. So this will be, so we have 4 squared plus 2 squared plus 5 plus, so these 2's are going to cancel. So this is just going to be x over, so our x is 4 over square root of x squared plus y squared is 5. And this is x minus 4. And this is plus, so those 2's are going to cancel again. So this is y, so that's 2 over square root of 4 squared plus 2 squared plus 5 multiplied by our difference in our y. This is equal to, so this is 16 plus 4 plus 5, which is 25. So this is square root of 25, which we know just to be 5. This is plus 4 over 5, x minus 4, plus 2 over 5, y minus 2. And when we distribute this, this becomes 5, and it's 4x over 5 minus 16 over 5 plus 2 over 5y minus 4 over 5. Let's simplify this even more. So the linearization as a function of x and y is going to equal, so this is equal to 4x over 5 plus 2 over 5y, and this is plus 1. Okay, so that is our linearization equation for part B. And we'll finish this question up with C. Okay, and then we'll do one more differential question. Okay, so let's do part C. So we're going to start with our same form. So let me just write this out so we don't lose track. Okay, so we'll start out with this first one. So this is equal to y times e to the power of x plus y squared. And this is plus. So partial derivative, so this is going to be y and e plus y squared. Right, and this derivative would come down, that would just be 1 for x, so then this just stays the same. And this is times our delta x, so our x variable minus our initial point, which is negative 4, minus negative 4 is plus, and this is plus our final partial fraction. So this is plus y squared. This becomes 2y squared at the front. And this is times our y minus 2. Okay, so if we plug in for our variables here, y becomes 2 times e to the power of negative 4 plus 2 squared. This is plus 2. Do the same thing, so that's negative 4 plus 2 squared. That's x plus 4. And this is plus 2 squared e to the power of negative 4 plus 2 squared y minus 2. Okay, so this is equal to, so this is just going to be 0 in the exponent, so that's just going to be 1. So this is 2 plus 2 times x plus 4, and this is plus 8, and that's y minus 2, and this is equal to, actually, yeah, we can stop it here, but I want to distribute it, so this is 2x plus 8 plus 8y minus 16, and this linearization equation is equal to 2x plus 8y, and that's negative 16, plus 8 plus 2, that's negative 6. Okay. So now this last question here is using differentials. So we are going to start with this question here. All right, so we have a rectangular box with a square base. So if I were to draw this here, so our square base has side lengths x and x, base length, and its height is y. All right, so if its height is y, then our volume would be our base times our height. So our base is x times x, which is x squared, times our height, which is y. Okay, and we want to find what our change in v is. So our change in v is equal to our partial derivative with respect to x times delta x, and this is plus our partial derivative with respect to y times delta y. In this case, this question is very kind to us because it gives us our delta values. So our delta x is equal to, so we're increasing by 1.5%. And in our y, we are decreasing. So because it's decreasing, we're going to put a negative, and that's negative 1. So if we were to write this out, this would be, so with respect to y, this is 2xy, and our delta x is 1.5, and this is plus, so this is going to be x squared now, if we do it with respect to y, and this is times negative 1%. Okay, and if we, sorry, let me rewrite this. I apologize. Sorry, since this is a percent, this means that our change in x over our original is equal to this variable here, and our change in y over our total y is equal to that. I apologize. So if I wrote this out, still the same here, it's equal to, so I'm going to write this again. So this is our delta x plus x squared delta y. And if we took each of these terms and we're going to divide it by its volume, right? Volume we were already given up above. So this is going to be now equals, so this is 2xy delta x over x squared y plus x squared delta y. So this is meant to be delta y up here too. Over x squared y. We say that this is approximately equal to, so let me just draw this over here. This is approximately equal to our, so this term right here is equal to our delta x over x, and this is plus our delta y over y. Right, and the reason we divided by this volume is so we could get the same kind of ratio for this, where we had our change over our original to get that percent value, because we want our final change to be a percentage for our volume. So this is equal to This is 2 times 1.5 and plus -1, which makes our value for our percent equal to 2%. Okay, so that is this question here. Right, and that brings us to the end of our examples for this unit. So feel free to go back to some of the ones that I skipped over and try them for yourself. Right, and I hope this helps you. And just pay attention when you're doing these questions. Be careful and take it slow. And yeah, that's it for today. Thanks for watching.